Have you ever just stopped and noticed the rhythm in things? A guitar string vibrating, a child on a swing, even the sway of a skyscraper in the wind. They all share this hidden pulse, this fundamental dance of the universe. Well, today we're going to pull back the curtain on that rhythm. Physicists call it simple harmonic motion.
Take a look at this. It seems so simple, right? Just a block on a spring, bouncing back and forth. But inside this simple motion is a secret, a really precise mathematical story. And it's the same story that describes sound waves, pendulums, even the orbits of planets. So the big question is, how do we read that story?
Okay, so before we dive into the deep end, let's start with the most basic idea of all. What do we even mean when we say a motion is periodic?
Just think about the pendulum on a grandfather clock. It swings back and forth, crossing that bottom point, moving in the same direction with this perfect, steady timing, over and over again. That's it. That right there is the essence of periodic motion. It's the predictable, steady heartbeat of any oscillation.
All right, now that we've got the basic concept down, it is time to learn the language of this wobble. And you know, in the world of physics, that language isn't spoken in words, it's spoken in equations. Now, I know what you're thinking, a bunch of Greek letters, right? But trust me, this is so much more than that. You should think of this equation as a complete sentence. It tells the entire story of that block's journey through time, all packed into one beautiful, elegant line, and we're going to learn how to read it.
And just like any good story, to understand the plot, you gotta know the characters. So let's break this thing down piece by piece and see what role each part plays in this drama of motion.
First up is amplitude, that X. This is basically how big the swing is. How far does our little block dare to travel from its comfy home in the middle? Notice how the two waves here have different heights. That's different amplitudes. But check it out, they still finish their back and forth in the exact same amount of time. Next, we have frequency and period. These two set the tempo of our story. It's like tapping your foot to a song, you know? Frequency is how many taps you make every second, while the period is just the amount of time between each tap. They're two sides of the same coin, and they control the rhythm of the whole thing. And finally, we have the phase constant, phi. This one's actually pretty simple. It's just the story's starting point. It tells us exactly where the block was in its cycle the moment we hit go on our stopwatch. Think of it as the once upon a time of the equation. Okay, so we know where the object is at any given time. That's huge. But what about how it's moving? How fast is it going? And what's the push and pull that's driving it? And wow, this right here, this is where it all comes together. This shows us how the object's position, its speed, and its acceleration are all connected in this beautiful flowing dance. Let's zoom in on the most important moments. So think about it. Right at the very edge of the swing, the block just hangs there for a split second. It has to stop to turn around, right? So its velocity is zero. But at that exact moment, the spring is stretched to its absolute limit, yanking it back. That is maximum force, which means maximum acceleration.
Now what about when it flies through the center? It's a total blur. It's moving at its absolute top speed. But for that one brief instant, the spring isn't stretched or compressed. It's perfectly balanced. There's no force on it at all, so its acceleration is zero. Isn't that wild?
And that's the whole secret. This is the heart and soul of simple harmonic motion. It's this constant tug of war. The further you pull the block away from the center, the harder the spring pulls it back. This relationship, where the pull is strongest when it's furthest away, is what creates that perfect, repeating rhythm. So this constant pull, this engine that's driving the whole show, it actually has a special name. And understanding it is the key to unlocking why this whole thing happens in the first place. It's called the restoring force. And for a simple spring, it's described by Hooke's law, F equals negative kx. Now, don't just glance over that tiny minus sign. That minus sign is everything. It's the mathematical guarantee that the force is always fighting to return the system to the center. It's the hero of our story.
All right, let's switch gears for a second and look at this whole dance from a totally different angle, energy. Because what's really going on here is this constant trade-off, where energy is just being passed back and forth, but the total amount never ever changes.
So let's think of it like two bank accounts. You've got kinetic energy, that's your checking account. It's the energy of motion, the energy you're using right now. And then you have potential energy. That's your savings account. It's all that energy stored up in the stretched or compressed spring, just waiting to be spent.
And this chart just captures that exchange so perfectly. See, when the block is way out at the edges, it stops moving. The checking account is empty, right? All the energy is tucked away in savings. But then, as it flies back toward the middle, it's cashing in all that savings, turning it into pure motion, hitting a maximum right when it passes through the center.
But here is the most beautiful part. No matter what the individual balances are in those two accounts, if you add them up, the total amount of energy in the system is always constant. It's a perfect, closed system. The energy just cycles back and forth, forever.
Okay, theory is great, but now it's time to put our newfound knowledge to the test. Let's take everything we've just talked about and use it to analyze a real oscillator and predict exactly what it's going to do.
So here's our challenge. We have an oscillator. We know its mass, how far it swings, and how long one full swing takes. The question is, can we use what we know about SHM to figure out the rest of its secrets? The answer is absolutely yes.
Let's walk through it. Step 1 is a gimme. We know the period is half a second. Easy. From there, we find the frequency, just 1 divided by the period. That's 2 Hertz, which just means it goes back and forth twice every second. Simple enough. Next, we find the angular frequency, omega, which is really just a way of measuring cycles that makes the math work out nicely. Once we have that, we can figure out the spring constant, K, a number that tells us how stiff the spring is. And finally, we can use omega to calculate the object's top speed. See how that works? Each piece of the puzzle lets us find the next one. So we've seen how a simple block on a spring tells this incredibly deep story of force, energy, and rhythm. It really makes you wonder, doesn't it? If we could just learn how to listen closely enough, what other symphonies of motion, what other invisible stories are playing out all around us, from the silent dance of atoms to the grand, sweeping orbits of galaxies?